He will talk about mixed populations.
Okay. So, first of all, thanks a lot for the invitation. Nice to meet you. And so today I'll talk about mixed interpolation, and well, the idea is that here you have like Craig's interpolation for classical propositional logic, which is stated as follows: if the formula phi is satisfiable, a formula psi is falsifiable, and phi interval psi, then there is a formula P containing only atoms common to phi and psi, such that phi entails chi and chi entails psi. So here, this is what we can call a sort of pure interpolation theorem in the sense that here we're only working with a single logic, which is classical logic. I mean, and the idea is that, yeah, this theorem holds true within classical logic. Now one might ask, the following question, talking about mixed interpolation theorems. What happens if you have the following proposition, for which logics X and Y does the following mixed interpolation theorem hold? If a formula phi is classically satisfiable, so here we're just considering the classical case first, is classically satisfiable, a formula psi is classically falsifiable, and phi classically entails psi, then there is a formula chi sharing all its atoms with both phi and psi, such that phi entails chi in the logic X, the first logic that is undefined for the moment, and chi entails psi in the logic Y. So, of course, I mean, answering this question would be way too much, so we'll restrict the cases and we'll only look at some orthogonal three-valued logics. And what's interesting also about such a proposition is that if here you have logic X and the logic Y, which are subclassical, then you have some kind of refinement of Craig's interpolation theorem. Yeah, because if X, if the valid inferences of X and the valid inferences of Y are subset of classical logic, then you get some kind of a restricted version of this interpolation theorem. So we'll answer the previous question that we asked for any two propositional logics based on the same three-valued Boolean normal monotonic scheme. So I'll go back to that for the connectives and two possibly identical monotonic consequence relations. And again, since these two, the logics that can be defined in such a way will be subclassical, any positive answer to the question must be seen as a particular refinement of Craig's interpolation theorem. And then we will present some characterization of the set of classically valid inferences as the relational composition of any two monotonic logics based on the same normal monotonic scheme for which the mixed interpolation property holds. So the background to these works are first the works by Miles and Presnodel, proving that the mixed interpolation property holds for the pair K3 and LP. So the idea is that here you get, if you input, I guess input K3 and LP, they manage to show that the property holds. And so this is a particular refinement of Craig's interpolation theorem. So what we'll see is that just note that K3 and LP are particular cases of logics based on monotonic consequence relation and Boolean normal monotonic scheme. So basically, we'll extend somehow this result to many other logics. We'll also use the recent work by Bruno, Damien, Polegay, and Emmanuel Schermer, showing that all the three valued logics based on an ST consequence relation, and I'll go back to this definition later, and the Boolean normal monotonic scheme coincide with classical logic. And finally, this is also linked to a paper that we are preparing with Polegay on the characterization of the set of ST valid inferences as the relational product products of basically K3 and LP, and the set of TS value inferences as a rational sum of LP and K3. Okay, so let's start with some preliminary definitions.
Can you go back to the definition of Craig's theorem in the classical case?
Yeah.
So how are you using the notion of satisfiability for the classical case?
Yeah, there is a valuation that all the formula phi to go to 1 and psi to go to 0. So phi is not a contradiction in some sense in the classical case, and psi is not a tautology. So yeah, we'll just start with a very basic propositional language, the classical one, using negation, disjunction, and conjunction. We'll define an inference just as a pair of two sets of formulas, finite sets of formulas. And then we have all these definitions of consequence relations. So the idea is that we will define a logic as a combination of a consequence relation with a boundary standard and also a scheme for just the connectives. And so here you have all the intersective mixed consequence relation that are also defined monotonic consequence relations for three-valued logics. So you have the SS validity, where basically you're moving from 1 to 1, the TT validity, where you're moving from 1.5 to 1.5, the ST validity, moving from 1 to 1.5, the TS1 from 1.5 to 1, and the intersection of the SS and TT validity, which requires that an inference is valid. And this is, sorry, I didn't mention that, but it just means the symbol is used just to say that the inference is valid. If and only if the inference from gamma to delta is valid in SS and is also valid in TT. Then we have the notion of Boolean normality, which is, again, quite straightforward. The idea is that given a particular operation, if you look at the scheme or the tables of the connective, in a three-valued logics, all the classical values should be the same, basically. So for all the classical cases, the operation or the computation of the result of using the connective should give you the same thing as classical logic. Now, following Darren Hall, we will define an order, some kind of informational order on the truth value. So a half is less than 1, a half is less than 0, and we define a component-wise ordering based on this particular order. And we will write down the following: if and only if all A1 is lower or equal than B, and so on, up to AN lower or equal than BN. And that allows us to define the notion of Boolean normality, which goes down to the following. The idea, again, is that given a particular sequence of A1, AN, which is such that A1 is lower than B1 and so on, then the operation, the application of the operation to A1 to AN is lower or equal to B1 to Bn. And so one of the nice, let's say, interesting property of such operation is that if you have, for example, B of phi, which is 1, which takes just a classical value, and let's suppose that you have a P, which is an atom of phi, which take the value of half. If you take a valuation P prime, such that P prime of P is different than a half, and B prime agrees with B on every classical truth assignment to the items of phi, then it should be the case that B prime of phi is 1. That's the idea behind this notion of monadicity. Okay, so here are the 16 Boolean normal autonomic scheme that we get from these two particular definitions, which are illustrated by the following matrices. And note that the commas that we have here, 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 and here are also a particular choice. That's why basically we get 16 different truth tables within this one, depending on the choice that you're making here in sources. So here you have the famous Strong-Linie scheme, and combining this scheme with the relation, the consequence relation SS gives you K3, and combining this scheme with TT, you get LP, ST, you get ST, TS, and SS, intersection of SS and TT, you get Kalman implication. Then you have the D scheme, which is a bit less known, which is the middle cleaning scheme, which is mostly used to account for presupposition projection in semantics. And the idea is that what you get here is a non-commutative disjunction and non-commutative conjunction and non-commutative disjunction. And one thing is that we will say that given such a scheme, the logic based on this scheme will be left infectious, in the sense that if you have a formula that starts with any atom, if the atom takes the value half, then the whole formula will get the value half. That's the idea. So we also have like the right version of such a scheme, and also any possible combination between the same. And then we also have among the famous scheme, the weakly scheme, which is fully infectious, in the sense that if you have a formula and any atom takes the value half, then the whole formula will take the value half. And it gives rise to combining the relation SS with this scheme gives you weak K3 and paraconsistent weak K. So the idea is that now we have the schemes on the one hand, we also have a definition, some 5 different definitions for the consequence relation. We will analyze the logic that arises from them, and we'll see whether by inputting these logics into the mixed interpolation theorem that I presented before, the property holds or not. And so in order to refer to this kind of all the different schemes, we will combine the following notation. So for example, here you have a choice. So remember that in the matrix that I presented, we had a choice between 2 possibilities. And the idea is that here the possibility will be settled for conjunction. Here in such a case, it will be, the conjunction will be the conjunction of Strong-Linie, the disjunction of Strong-Linie, the conjunction of weak-Linie, and so on. And here you have the conjunction of left middle Linie, and so on. So here are some examples. Of course, if you take the Strong-Linie conjunction and the Strong-Linie disjunction, you get just the Strong-Linie scheme, middle Linie here, and weak Linie if you take weak Linie for the conjunction and weak Linie for the disjunction. Okay, now let's come to mixed interpolation, and let's restate our the property in question that I mentioned, this mixed interpolation property, and we'll wonder for which C, which will denote the monotonic consequence relations that we defined earlier, and which X that will refer to the scheme, for which combination does the property hold. And so here is first some kind of direct answer that we can give just looking at the consequence relation. So here, if you have a cross here, it means that the property won't hold, no matter what, independently of the scheme that was chosen. Here you have only one cell which is marked with a check mark. It is the combination of ST and ST. No matter what you'll get here is that the property will hold. I'll come back to this one just in a second. And finally, you have like this slice, two possibilities, which indicates in some sense that it will depend on the scheme that you're choosing, whether the property holds or not. So yeah, this is what I just said. Here for this particular case, it will just mean that for some schemes, the property will hold, and for other it won't. Okay, so here is an example of failure of the property. So you have the following inference, which is classically valid. But one can show that there is no chi composed only from the atom P, which is the only atom which is common to the antecedent and the succedent. This is only P. And there is no chi composed only from P, which is such that it is the case in TT, given any scheme you want, and chi will be such that P or Q and not Q entails chi, and in SS, chi entails P and R or not R. Just take P as an example, as a simple case, and give Q the value half. So it means that this whole thing will take the value half. P will take, let's say that P takes the value 0, and 0 or half in all of the schemes give you a half. And on the other hand, remember that here we have P will take the value 0, so it just won't work. And in any case, you cannot construct such a P which will be only composed of the atom P, and such that such a property holds. An example of success, there is basically only one, which is in the case where you have independently of the scheme that you're choosing. If you have an ST, if you're composing an ST consequence with an ST consequence, then you'll get directly that the property holds, mostly because, again, we'll rely on the work by Darrell et al., showing that, yeah, basically ST, if you have on the one hand a Boolean normal monotonic scheme and an ST consequence relation, then you get all the inferences of classical logic, which means that basically if you take ST, the combination of ST and ST, what you'll get is just Craig's interpolation theorem. And of course, it holds. Okay, so we'll just focus on this particular cell because we'll see that these two other ones boil down in some sense to this one, can be reduced to such a case, and also that this case is some kind of refinement of the others. So we'll kind of zoom in here and just look at the scheme that we have that can be used when you have on the one hand a logic with an SS consequence relation and a TT consequence relation. And here is the property restated where SS and TT are fixed, and we will check for which scheme does the property hold. And here is basically the answer. For 8 of the cases, the property will hold, and for 8 others, well, it won't. So, of course, if you have a strong Kleene scheme, it will hold. A weak Kleene scheme, it will hold. But if you have a middle Kleene scheme, then the property won't hold.
Sorry.
Yeah.
The satisfiability and unsatisfiability conditions are stated in terms of classical logic for every logic that you are interpolating.
The first condition?
Yeah.
Yeah. It will always be classical logic here that we'll consider in the following property. Yeah, this one. Here you have CL, which is classical logic.
Okay.
Yeah. And phi entails psi in classical logic. The only things that are moving here are, I mean, in such a case, since we fix the SS and TT case, are just the scheme that we will pick, whether it is the strong clean scheme, the weak clean scheme, or the middle clean scheme. And so, in order to show that all these cases fail, we'll rely on the following lemma. For each of the logic, basically, that arise for all the formulas which are analyzed using a scheme marked with an X, with a cross, we will have the following lemma, that V and V prime be two valuations based on the same scheme marked with a cross. And if you have a valuation that attributes the value a half to P, a valuation V prime that attributes the value a half to Q, then for all phi of the language, if phi is only composed of the atom P and Q, and then it will be the case that V of phi is a half, or V prime of phi is a half. So, yeah, the idea is that if you have a formula, and this formula is only composed of P and Q, then in such a case, it will always be the case that you will have one of these two valuations that will attribute the value half to phi. And so given this, we can show that the property won't hold if you're picking a middle clean scheme. And just by showing that there is no chi composed only of the atoms P and Q, such that chi entails the following formula. And again, this is the succedent of the following classically valid inference. From P and Q, you can infer R and Q, or not R and P. So how does that work? Well, basically, you get these two valuations. R takes the value 0, Q takes the value a half, which means that here you get the value 0, because again, we're analyzing things in middle clean scheme, which means that if you in a middle clean, if you have 0 and a half, you get 0, but the other way around, if you have a half and 0, then you will get a half. Which means that here you have 0, of course, 1 and 0, since the scheme is Boolean, normal, then you also get 0, so the valuation will attribute the value 0 to such a formula. And if you take V prime and you attribute the value 1 to R, 0 to Q, of course, you got 0, and again, 0 and a half gives you 0. So in both cases, the formula will take the value 0. And given the previous lemma, since you have two valuations such that Q takes the value half for the first one, and P takes the value half for the second one, then it means that there is no phi that you can construct only from P and Q, which is such that phi doesn't take the value half. Or for all possible construction of chi, in this case, from the atom P and Q, then chi will always take the value half for at least one of these two valuations. Okay, which means that in some sense, given this particular property, there is no way to construct such a chi independently of what's going on there in the other half, in the SS part that you have here. No matter what, it will be just impossible to build such a chi, which means that in this case, in the case of left middle cleaning, the property just won't hold because there is no possibility of building, of constructing such a. And so, given some adjustments of the succedent, such a result also holds true for the other schemes marked with a cross. So basically, here you have such a formula, you can play a bit with the connectives, and basically you get a formula that will have the exact same property. And yeah, which means that any combination of a logic with a TT logic based on a scheme marked with a cross fails to satisfy the mixed interpolation theorem. Hence, the combination of an ST logic with a TT logic fails in at least 8 cases. well, because you will have, if you take for the first logic of the interpolation ST, the second one you take TT, of course you won't be able to get a chi that will somehow bridge the antecedent and the succedent. The same thing holds true for all the SS logic. In 8 cases, it will be the case that it is impossible to build such a chi. And so again, we have the following valid inference, and we can show that there is no way in, again, left middle key, there is no way to construct a chi. Again, you have 2 valuations, v prime, 0 or 1 gives you 1, 1 or half gives you 1 in left middle key, which means that this whole formula will take the value 1, and given our previous lemma, either by v will give chi the value half, or v prime will give chi the value half. And the same thing goes for v prime. Which means that again there is no way to construct such a chi. And this gives us all these cases which are now settled, because so of course in this case for these 8 cases which are here, there is no way to construct a chi because of TT, here is because of SS, and here again is because of TT. Now, maybe the most interesting case is where indeed the property holds. And if the property holds, we need some kind of way to build, to construct the interpolant. And we will use the following definition. What the following definition is saying is that take any Boolean normal monotonic scheme, and we note P tilde to denote a literal, is a P or not P. And you take phi to psi as an inference, such that phi is satisfiable. And then you build a C, which is only composed of literals, of the conjunction of literals, which are both in phi and psi. So atom phi just denotes the set of atoms of phi, and atom psi is the set of atoms of psi. And we'll say that such a conjunction of literals is admissible with respect to this particular inference, if and only if you can find an X valuation where X is a scheme, V such that, of course, V of C takes the value 1, V of phi also takes the value 1, and here is something kind of new, which is very particular to such logic, because so far if you don't have this, you have the usual way to find the interpolant of Craig's interpolation theorem. Here what we're adding somehow is the following. If Q is both in phi and psi, but not in C, it means that Q takes the value half. So what will happen is just that you will find the interpolant as for classical logic, except that you will remove from the conjunction all the atoms that take the value half. We'll erase them and we won't take them into consideration. And so given this, in order to build the interpolant, let's just start with the weakly case, which is the easiest one. We just take the disjunction of all the C admissible with respect to the inference in question. For any scheme that ends with a strong linear disjunction, any combination here, you can put anything you want. We take the disjunction of all the De Morgan equivalents of the C admissible with respect to phi to psi. I will come up with an example in a second. And here we take the De Morgan equivalence of the disjunction of all the C admissible with respect to phi to psi. So now here is the example. We'll use the following inference, which is classically valid. And we will analyze such an inference using the following scheme: left middle Kleene. So this is the conjunction of left middle Kleene and just the disjunction of strong Kleene. So we'll start by writing down the first valuation that makes true the antecedent, and we'll write down P and Q, and we'll ignore the R, okay, because R takes the value half. then you have the following valuation that also makes through such a formula. And again, we add a disjunction and P and Q and R. And also this one, and this is the last one. And then we check whether such an interpolation that we constructed allows to entail the consequence. And in such a case, well, it doesn't work, because if you just look at this element and such evaluation, here you have a half, a 0 and a half. With a middle Fini conjunction, you should get 0. You have 1 and 0, so you also get 0. This whole thing get the value 0. And if you look at just this thing, you see that you have a half and 0. And in middle Fini, it gives you a half. And if you have a half here, then the whole thing should take the value half, because you have disjunction. A half here, this should be also a half, and so on. So you get basically a counterexample to such an inference, because this thing will take the value of half and this one the value 0. Switching these two elements won't change, because you can also find a valuation that will produce exactly the same thing, and the solution will be indeed to take the De Morgan equivalence of each C, which is a conjunction of its rows. And in such a case, it will work, because we know that since you have a strong Fini disjunction, then basically the order shouldn't matter. The connective becomes associative, commutative. Sorry. And yeah, in such a case, we have the following interpolation. So for any scheme, the set of valid inferences of a logic based on an SS or TC consequence relation is a subset of the set of valid inferences of the corresponding SC logic, which means that whenever the theorem holds for a pair of logics based respectively on SS and TT, it also holds for a pair based on SS and ST, ST and TT, and ST and XT. And that's why these cases, the 8 cases that we considered before, are just some kind of refinement of these other cases. Yeah, and so we have all these cases. This one is the most important one, and these 3 other ones are just some kind of extension. And again, given that the logic discussed above are all subclassical, what we get is some kind of strengthening of correct interpolation theorem. And among the 40 positive results that we have, 8 are more refined than the most. And these are the 8 most important. Okay, further results. Even slight modification of the proofs that we used before, we can show that for any scheme X marked with a check mark, if the inference from gamma to delta, where gamma and delta are set of formula, is classically valid, then there is a formula chi such that gamma entails chi in a logic with an SS consequence relation and any scheme marked with a cross, and chi entails delta for any logic with a TT consequence relation and the same scheme as this one marked with a cross. So how does that work? Very briefly, the limit cases can be are very easily to treat. Basically, remember that we had a condition, a variable sharing condition. We can basically drop it in such a case because we know that you have some, you can construct an interpolant sharing all its variables with the antecedent consequent. And finally, well, you can also turn the inferences from formula to formula to inferences from set of formulas to set of formulas. You can also show, and that's interesting, the other direction of the lemma, independently of the choice of the scheme. So take any scheme you want, basically the consequence relation will do all the job. So yeah, the idea is that if you know this, if you know that gamma entails chi in SS and chi entails delta in TT, then immediately you get that the inference is valid in classical logic. So we'll just denote the set of valid inferences of all the logics that you can build from this thing. So here you have SSX, which denotes the set of valid inference of a logic based on an SS consequence relation, and X denotes any Boolean normal monotony scheme, and so on. And here is what you can show by combining our two previous lemma, which is that for all Boolean normal monotonic schemes marked with a check mark, the set of classical valid inferences is identical to the set of ST valid inferences in such a Boolean normal monotonic scheme. I mean, this is the result from Lindar et al. And also, and this is new here, basically you take the composition of these two sets, the set of SS valid inference in a scheme marked with a cross, and the composition, you compose this thing with the TT consequence, the set of TT valid inferences in a scheme marked with the same cross, and basically by bridging the two, you'll get that this is the set of classically valid inferences. So here, in general, what you'll get here is a paracomplete logic, and here you'll get a paraconsistent logic, and by bridging the two, taking the composition of the two, you retrieve classical logic. And so as a matter of example, you can define classical logic as the composition of the set of valid inferences in weak case tree with paraconsistent weak limit, and also the set of classically valid inferences as the composition of case tree with L in a strong limit. Yeah, and so here's the conclusion. We presented some results strengthening Craig's interpolation theorem for classical propositional logic. These results extend the refinement of the interpolation theorem proved by Mind and Presnozil. And because they only showed it for the case tree and LP, and we extended these things to all the consequence, the monotonic consequence relations, as well as the Boolean normal monotony schemes. And among the 400 possible combinations of the two three-valid monotonic logics based on the same Boolean normal monotony scheme, only 40 satisfy the mixed interpolation property, 8 of which are just a stronger refinement of Craig's interpolation theorem than the others. And finally, we then extended this result to show that these 8 combinations allow to define classical logic as the composition of an SS logic with a TT logic, given that both are based on one of these 8 schemes. Yeah, thanks a lot.
Questions? I mean,
Yeah, thanks Dan for the presentation. Really loved it. So I'm going to go beyond this and ask you about things that you didn't mention, just out of curiosity. What about the non-monotonic schemes? Have you played with them? Do you have any insight? Something that is perhaps interesting about those cases?
Yeah, no, I haven't tried it for the non-monotonic scheme, and this is something that I should do. The thing is that the proofs relies heavily on the use of the fact that the schemes are monotonic. And I'm not sure that this will work, but of course we would like to find a particular characterization, and to see whether in general, or that would be, if that would fail for non-monotonic.
But interestingly, one of the sides of your proof doesn't rely on the monotonicity.
Yes, not at all. It only relies on the consequence relation. And that's enough to have SS and TT. So yeah, thank you.
Camilo?
Yes, I also love the talk. So I was wondering also about a possible future work. So I was amazed by the fact when you showed the table with the crosses and the X, and I was amazed by the fact that there were some non-commutativity going on. So SS and TT can validate the interpolation, but TT and SS cannot. So I was wondering, to deepen our understanding of these families of logics, if it is possible to find some other kind of property of interpolations where we do not talk about validity, but perhaps anti-validity or invalidity or something different, that allows us to find, let's say, the symmetric results. So results which should hold for TTSS, for example, but not for STP. Just.
Yeah. You mean, for example, for the anti-validity?
Yes.
And yeah, so I've been working on that a bit lately, and the idea is that, again, we can use kind of composition if you want to define the anti-validities of TS by taking, under some conditions, but basically by taking, in the case of the strong Kleene scheme, by taking the composition of the anti-validities of LP and the anti-validities of K3. And that will work to get all the anti-validities of TS, which are way more interesting than the anti-validities of ST.
Sure.
Yes, I really like the work. And related to Damian's question, I think for the many non-normal schemas, with the TT consequence relation, for instance, you obtain classical logic, for instance. And for the SS consequence relation, you obtain classical logic. So maybe you can have the result for many schemas, more than this monotonic.
Yeah.
So it's very promising.
I think that it will, for example, work for the collapsible schemes. I mean, I see no reason why they are kind of almost trivial in some sense, because so the idea is that the value half collapses with the value 1 or 0 in all the cases. And yeah, I think that this thing will also hold for such schemes. Yeah.
Thank you, Nina. I really like it. Maybe you said this and I forgot it, and I think that Bruno's question presupposes the answer. Does this holds for all and only the cases in which the combination gives you the logic on the first part and the logic on the second gives you classical logic? Like STD will be ST, and which is in sometimes classical logic, and also for the weak Kleene case. So is it always that you at the end up having something like classical logic?
So I mean, it will depend on the scheme. For one part of the last part of the proof that we have, basically, if you have an SS consequence relation and CT consequence relation, which then you automatically get classical classically valid inference. The other way around really depends on this. And yeah, so one part only depends on the consequence relation. That's okay, which means the mix is way easier. The other part is really dependent on the scheme that you
Hello, do you have a question?
Yes, thank you. Yeah, thank you. That was a super interesting talk. And I mean, I didn't know even that anyone thought about this mixed interpolation. Super interesting. Another case that, I mean, follows basically trivially, I don't know if it's in the literature, is with intuitionistic and dual intuitionistic logic for proof theoretic reasons. Because, I mean, classical logic is a fragment of intuitionistic logic and of dual intuitionistic logic. And you get LJ by getting just one formula in the conclusion, and dual LJ with one formula on the antecedent. And so by getting the interpolant for a sequence that has gamma and delta with 1A, then you get, yeah, two derivations, one in LJ and one in LDJ. But yeah, the other thing I thought, I mean, it's super interesting for specifically your work on trivial logics for other two reasons, I think. One I think Camillo mentioned basically, because I mean, usually in interactive theorem proving or other things like that in computer science applications, let's say of interpolation, it's not used this property, but the classical equivalent property that of which, like, if two formulas, one is like are together, unsatisfiable, right? Then you can get the interpolant. So, but that would require probably anti-validity and things like that, right? So it's already interesting, like the duality. I mean, because in classical logic, of course, right? You have it already. Whereas here, maybe you can get like a class that is like computation-wise better or whatever. And the other thing, I mean, interpolation is always like the dual of cuts, right? If you have an interpolant, you surely are going to cut it, right? But this is very interesting in this case because you get all the cuts, or, I mean, some cuts at least that are valid in ST, right? And
Yes.
I mean, right?
Yes.
What about that? You have like some class of interesting cuts. I don't know if you can get out of this. I don't know.
So one thing about cut and I didn't mention is that basically you can get the following. So here you have instance of cut. Some space. I don't know. Let's use this.
Yeah, no worries.
And so the idea is that if you have this, you can if and only if you have gamma, sigma, delta, theta.
Just a second, I cannot see your video for some reason, but yeah, okay, maybe now. Okay, yes. If there was a moment, just a second, let the camera go there. Okay, now I can see it, yes. Okay.
So yeah, the idea is that basically you can get the following kind of version, cut-like version of the theorem that we have. So rather than working with a single formula here, you just take the following version of, the statement of cut, and you have this equivalence between classical logic and an SS consequence relation with an X marked with
and the other one is TT.
mark and so on.
Ah, that's very interesting. That's very interesting. That's super interesting.
You have a version of cut given that your inference, and let's say that, indeed you can write ST.
Yeah, of course. Yeah,
also working, And so the idea is that you will retrieve cut given that your inference here is SS valid and this one here is TT valid.
I see.
It means that you have some kind of a version of cut. So of course this version is a global version of cut. But if you add, like, let's say, a lambda for non-classical value, this will also work.
Ah, I see. Okay. And phi, so the phi there is an interpolant, right?
Yes, exactly. So
I see. That's super interesting. Is it like published, this result already, this proof, or?
No, not yet.
Okay. But that's super interesting. Thank you.
Thanks.
Direction also?
Yeah, it's an even only.
Okay.
So this one from there to there is given just by the consequence relation. This one will depend on the scheme.
So I have a question. So probably you have thought about this, but there are other logics built with other standards from this pre-value setting are also monotonic. For example, the one that preserves value 0 or the one that preserves non-true. So we thought about that. Can these results hold for those logics because they are monotonic and the constants behave the same? Probably the ones that are the complement of SS and TT also are important.
Right. So no, I didn't check whether it was the case. I don't feel like the monotonicity of the consequence relation plays an important role, but I'm not sure. But yeah, I'll
Is there any other question? Here you go.
So it's just a curiosity, but So when we speak about interpolation and classical logic, so I think about, for example, the results with FDE, for example. So have you thought about like what happens if you extend this approach to the four-valued logics? Maybe you can use that as an aid to do the equations there.
Yeah, I think that would be the next way to go, just to start with four-valued logic, and these are some cases, at least like H3, LP are just super Belknap logic. So yeah, I think that using a four-valued logic would be preferable. But yeah, I just stick to three-valued logics for me.
You want to have one last question?
Excellent presentation. I have to think about some part of the result, but my curiosity is obviously if you check the other step in the hierarchies, combination of another criterion more complex.
So when it comes to the hierarchy, you can extend somehow these results to the hierarchy, showing that for, let's say, a level n+1, you can also find, like, take the decomposition of the two logics at the level n, just behind it, and bridging them will allow you again to retrieve the ST version, let's say, at the level n+1. So it's also working.
This is for the hierarchy that Damian, me, and Federico. But what happened with the other possibility combination, the levels, without maybe if you don't have the necessity to recover classicality or something like that? Maybe it would be a good idea to check the different combinations.
Yeah.
Because,
I'll definitely do that. Thanks.
Thanks a lot, Roland.
Conveniently, we have 5 minutes for you to go to the bathroom and for I to show you my handout. But most of you receive it in email, so you can read it on your cell phone. Because actually, I just printed 10 of them. So you can share them. Huh? Fight for them. But in any case, I have a presentation. So the only thing you have some definitions there. So if you want to look at them, you can but with this. We can take this 5 minutes to.
I am not in charge.
Oh, okay. You can take this 5 minutes and start at 6:30. Okay. Take conferences if you don't have. I don't know where I think if you have a one letter,
calculus of structures.
Thank you, Fede. Thank you all for being here. As the handbook explained, don't read it. Read it only if I mention or afterward, but all the explanations are in the slide. Okay. Let's start with some observations, preliminary observations. If you take a look at the original sequence calculus proposed by Jensen, you will see that they are defined over series. And one consequence of this is that in making relatively simple derivations, we have to use a lot of boring and interesting structural rules. So for instance, in order to derive this very simple thing, provided you are using when you want to derive this, you will have to permutate and contract a lot of things, but it seems obvious that the result was already here in the first step. So we all know that if we use a different version of the rules, the ones that we call multiplicative rules, we can get rid of these steps. So we just jump from the original premise to the original conclusion. Another way of doing this is to define the sequence as relations with simpler objects than series. So for instance, if I define the sequence as pairing multisets, I can avoid the use of permutations, and if I define the sequence as relation sum sets, I can avoid the use of contraction. In fact, these two strategies, the strategy of using other rules for the connectives and the strategy of using different structures in the nature of the sequence, are not equivalent. For instance, if I am using the version that uses the multiplicative rules, what I will have is that a rule like weakening is admissible in the calculus that absorbs it into the rules. But if I use the other strategy, what I will have is something a little more powerful. This is a permutation, not a contraction, thank you. Because in this case, the rule is doing absolutely nothing. The first part is absolutely exactly the same thing as the second part. So it makes the rule either potent. Yes. And the second absorption, in fact, is very strong. It's stronger than the first. So this is something that we already know. The more structure you have on the sequence, the less rules you need, and vice versa. So my first observation is this one. One day I was thinking about this, and I noticed that there is not an obvious way of absorbing the rule of weakening following this strategy. And the reason is that you get the sequence closed, so the terms of the sequence closed from the weakening, and you will have stupid rules like this one. It says that from the whole language to the whole language, you can derive the whole language implies the whole language. Okay, that was the first observation. The second observation is that we use the word structure in different ways. Jensen, for instance, defined structural rules, these three structural rules, and the rules of identity and cut are not part of the structural group of rules of Jensen. And neither is his characterization or his observation that you can obtain the logic Lj if you use the same rules as Lk, but you just never put more than one formula on the right-hand side of the sequence. So for a time, the use of the label substructural remained consistent with Jensen's terminology, but as we all know, today it is customary to call substructural also calculus that do not admit identity, do not admit cut, have constricted slots in one of the two sides of the sequence. So, and moreover, in everyday mathematical practice, structure usually means something different from everything I said by now. Usually, a structure in mathematics is understood as a set with a certain number of relations that this set works. with some properties of with certain demonstrable isomorphisms between the structures of this kind. And for instance, Joao Marco is not here, but last week in the CL and PSD, Joao Marcos noticed or observed that it is usual to call structural a logic that is uniform under substitution, and not all the other two meanings that we tend to use. That we are used to use. So the second observation is that it is not obvious how a structure is to be understood to encompass these three senses of structurality. So, given these two observations, what I want to give you today is the first draft of an idea that I have about encompassing all these things into what I call quite penantly abstract calculus structures. Actually, it's not a calculus, it's a theory, but we can discuss the name later. And this thing that I will present today has the intention to provide you with explications of the notion of structure, substructure, and superstructure that are precise and not just abstract talking. And I want this explication to be in harmony with the three uses that I just mentioned: the Gensenian, the Subtarskian, and the mathematical, general mathematical one. And most importantly, it may serve, and I will show that I will try to convince you that it does, serve as a basis for new forms of substructurality or superstructurality. So this is the structure of the talk. In virtue of time, the first part I will try to go as fast as possible, because it's not that difficult. It is just complicated the way in which it is written, but it's not that complicated. The most important part for us will be when we reach to logic. So, ACS, the abstract calculus of a structure, is completely made up with series. So definitions are given, lots of definitions make this notion precise. What you will find in the slides are the examples and illustrations, and if you want to know the details, you can look at the handout. We will presuppose an ontology, a collection. I am using collection in the sense that as we usually use the word set, because I need the word set to be used in the theory. This is what will give the theory its abstractness, because the ontology is given. What are series? Series are just lists of objects of the ontology surrounded by the angular parentheses. For the examples in these slides, I will be using Pokemons. So here are some examples of series. You have this series. This is also a series. It has only one thing. This is another series. It has twice the same thing. This is another series. This is something. This is another series. The important thing about this series is that it has repetitions in different orders. Okay, what you would expect of a series. The most basic operation between series is concatenation. And what is this to concatenate? Concatenate is just to put one series, the things in the same order of the first with the second. Nothing strange here. So the same idea. This is a series, and this is the concatenation. Okay. In the handout I put where I took the notations and the concepts from. This is nothing that I invented. I am just reselling you the hot water. And we have notation to say that something appears, not belongs, but appears in the series, and where it is in the series, because the series are supposed to be numbered. This will not have importance in this. So, given your series, we have two relations. Extension and equality. Extension is not extension in the sense that we say that something is extensional. Extension is a relation between two series. So if you look at definition 6, you will find that a series extends another if it is the same, but it has more elements to the right. So it is always to the right that you extend the same. So for instance, here we have an example. This is a series, and this one is a series that extends. It is also a proper extension because it has more elements. If it is the same, it just extends it, clearly extended because it is equivalent. And equality, it is just the property of having the same reactions. O sea, the same objects appear in the same position in both of them. Exactly the same positions in exactly the same. These are our basic toys, the series and the operations between the series. And we will define more. Now we come to the concept of a structure. So I said before, in ACS, we want everything to be made up of series. So this will include the notion of a structure. So a structure will also be a series. And this is the definition that we can find in number 8, that says basically that to make a structure, you need a collection. Remember that collection is referring to sets in the general mathematical sense, and relations. So you have a collection and a lot of relations, okay? And your collection must have all the series that validate the relation that come after. And what is important here is that it doesn't matter what is this relation. So for instance, some of you may know that there is a relation, an intentional with S relation between this series and this series. Some of you don't know. No. But it doesn't matter. This is important. It doesn't matter because we only need that this is a series between, a relation between series, okay? So I can have a structure within ontology that has a lot of series and relations that this series will validate, okay? The collection must be complete. And we will compare the structures. I haven't shown you an example because the example comes next. The structures will be compared in a rather stronger way than series. This is definition 9. The way in which we are going to compare two structures is that we will say that one structure is an internal substructure of another, not only if the second is an extension of the first, but the relations must preserve the previous relation. So here I have an example. Suppose you have this structure. This is a collection, this is a relation, this is the same collection, the same relation, and another relation. So we have extension, this is the first condition, but the second condition is that this must hold. So here you have that if S1 is related in R2 with S3, but S1 is related in R1 with S2, then this must be preserved in this square shape, okay? This is the original condition proposed by Russell when he presented the first idea of this thing in a book of 1990. So this is internal sub and superstructure. And now we will have external sub and superstructure. No, see. Here I got it from me. We will also have a soft comparison between structures. And the soft comparison between structures is a little more easier. You have two structures that begins exactly the same, differ only on the last element, and they will be externally substructures if everything that validates the first is validated by the second. So it is a relation, it is a subset relation in the common set theoretic sense. And obviously it depends on the specific definition of the final relation. You can then see the definition there. And definition 11, we will have equivalence between structures if the two are structurally, externally substructural to each other. Okay? Where are the examples? Miguel, where are the examples? We will see examples in a minute, but I want to go a little fast so we can see now the operations, and then we'll have plenty of time to comment on the example. So now that we have this, we have the series, then we have the structures, we have a way to compare the structures, and what we will do now is to present some familiar notions, familiar because we work with logic and we work with simple calculus, and this will be just a fancy way of presenting something that you all know, but in the jargon of this theory. And this will facilitate the transition to logic, but it is what we want. So for instance, if you look the handout, you will see that definition 12 defines something very stupid, that is the simple structure. And the simple structure is just a collection of series and the equality between series. So this is the simple. Or that's what you think. Okay. Permutation. What is a permutation? A permutation is an operation between series. Okay. And it is defined in number 13 in your handout. And what it does is to change places. Okay? So the permutation of 1 by 3 in the series just exchanges the elements. Okay? What will happen now is that we can identify series if one can be obtained by application of this operation from the other. And what will this give us? This is the relation of congruence modulo permutation. What you will have now is the definition of a multiset structure. And what is a multiset structure? If you look in your handout, definition 15, you can see that it is a structure that extends a simple structure. So you have your collection, you have identity, and now you have congruence modulo permutation. So a multiset structure is just a lot of series that get identified by permutation. We need some terminology to talk about when something appears in a multiset. This can be defined, how many times something appears in a multiset. This is useful, I think. Doesn't matter. It doesn't matter too much. What we want now is to go one step further and define a new operation that will be called contraction. And you know what contraction is. Contraction is just to reduce the number of things in a series. So you have a definition 17, that tells you how to reduce the number of elements, of elements in a series. And you have another one that is called anti-contraction, but that it is suggestively notated not with a C but with a W. But what it does is to augment the number of things in a multiset. So here we have an example. You have this multiset here, multiset structure, and we can apply contraction here, and we will obtain this one. This is abuse de langage because this should refer to a series, but I am referring already to the multiset.
Can you contract like a specific Pikachu?
Yes, you are contracting, but
You are contracting, yeah, but it
The
says
Pikachu?
Pikachu.
no, but it doesn't matter because in a multiset,
Which one?
because in a multiset you have identification modulo, and this is that kind of things are very important for what we want. Yes. So and the reduction of the number of Pikachus in the multiset obtains. So this was something to be expected. What is interesting about anti-contraction is that because in the way in which it was defined, you can augment the number of things that were already in the multiset, but you can also augment the number of things that were not in the multiset, because you have a definition, the definition that is prior to theorem 2, that tells you that everything belongs to a multiset. Only only that a lot of things will belong in a number of times of 0. So anti-contraction is defined completely general, so you can anti-contract things that are not literally expressed in the multiset. Okay? This is also something that will be important for. With contraction and anti-contraction, you can define progressive contraction. And progressive contraction, what it tells you is that you can augment or reduce the number of, you can iterate the operations of contraction and anti-contraction, but it has a bound. In the case of progressive contraction, you cannot reduce to 0 the number of things that were already in the multiset, and you cannot add something that was already 0 to make it appear, okay?
So isn't that exactly what you just said, that you can put something new?
If you use the operation of anti-contraction, but progressive anti-contraction is a different definition. Yes,
Okay.
This is in number 19. Okay? And with this, I can define another notion of congruence, and this will be congruence modulo contraction. And what is congruence modulo contraction? What you would expect is all the multisets that the multiset structures that you can obtain by progressively contracting from one another. And with this, we can define, unsurprisingly, what we will call a set structure. And this is what it is in definition 1. So, set structures are notated unimaginatively like this. Have precisely the relations that we want. They are insensitive to order, they are insensitive to the quantity of times that you put things on it. But you may say, Miguel, why are you selling us the hot water again? And the reason is that the part that is important here is that we are not proceeding from sets with more structure, we are proceeding the other way around. We are taking series as the original thing, and we are trying to build everything from series. Okay? And I will get to something that is new, I suppose. Mathematics, so I'm sure that somebody already did. But at least for me, this concept is new. This is the concept that appears in definition 22. That is the concept of a proliferation. Sorry. And what is proliferation? Proliferation is when you take something, as if when you took a set and you put more things in the set. Okay? It will be reflexive because you can put things that were already there, and you know that set structures are closed on their congruence modulo contraction. But you can put more. Okay, so this is the relation induced by the application of the operation of anti-contraction. And if you think this in your everyday set theoretic terms, a set proliferates into another if the first is a subset of the set. And here we can define a new structure that will be called the proliset structure. Unimaginatively, because proliset means a proliferating set. And what is a proliset? Is again a structure. Is this the structure that will have a lot of series as the first term, and then it will have the congruence modulo permutation, then we'll have the congruence modulo contraction, and then we'll have the proliferation relation. Okay? This structure, differently from the others, cannot be generalized into a congruence because it will happen what says in theorem 5. That it is that you obtain that every proliset structure is equal to itself, because you have that the empty proliset proliferates. This contains all the others. Okay. This is the last time that you will see the handout. So now you can just focus on the slides. I am not that good as also managing my time, but we'll see. Okay, so now a final example with focus. This series we have. Notice that I am using here normal parentheses for sets because now this is a collection. This is something that does not belong to the ontology of series. But it has a series inside, and the series are made with the things of our ontology. And this is a simple structure according to this theory. Okay, because it has this and a relation. This relation is identity. So far, so good. If we put these two series there, and now we consider congruence modulo permutation, we also have a structure. Okay, actually, we have a multiset structure. If I add to this structure the congruence modulo contraction, what I will obtain is something infinite in principle, but remember that the first term is collection. Collections are sets in the ordinary sense, so they can be infinite. And what will belong to this will belong. Remember that we're starting from big. To make this structure, we need to include all the sets that have only Pikachus and Raichus inside, but in any order that we want. So 3, 4, 5, 6, in any order, we'll have all them, and this will be this multi-set. No, the set structure. Claro, before we had a multi-set structure, now we have a set structure. And if you add the Broly set structure, you still have a structure. Only that you will have all the series such that there are some Pokemon, there are some Pikachus, and there are some Raichus in it. Okay. This is a Pikachu, this is a Raichu. They are a bit small, sorry. Now consider the following relation. This relation is validated if and only if every object in the all that is in the first series is in the second. Okay? You can extend the multi-set and the set structure with R1, and you will get a superstructure according to this theory. But if you extend the Broly set with this structure, you will fail, because in fact, you will lose the relation that we want, that is proliferation. So you will have that this is a subset of this one, but if you proliferate in both sides, you don't need to proliferate in the same way. You just have general proliferation, you will lose your relation, so this will fail. So you don't have a superstructure. But you have a structure, it's only different. It's not a superstructure of the other. But if you consider the relation R2 that says that gamma and delta share some elements, now you can extend all 4 structures with this relation. Okay? So, this is it. So far, this is what ACS is comprised of. Okay? Only a very fancy presentation of things we all know. Let's see how this relates to logic. Remember that what I want is a framework in which I can speak about the way in which we understand the structure and substructure in logic in a precise way. And I want that this is in complete agreement with the normal use of the concept. Okay? I love when philosophers present concepts, not that says somebody you are using it wrong, but when they say, now I understand how you are using it. So we don't want to dismiss anyone's opinion. So I believe that ACS provides such a framework, and I will try to convince you so. So let this Gothic L be a standard formal language for propositional logic. Don't read that. And let's consider this L as our ontology. Okay? The following definition is well motivated. A structure over this ontology is Gensenian if it extends a Broly-set structure. So you have Broly-sets, not only sets, but Broly-sets. And if you have a new relation between series that are closed under all the conditions of a Broly-set, what you will obtain is a Gensenian structure. Let K B dash models. This the usual relation of being the consequence relation of classical logic. And what you will find is that this one, the simple structure with this relation, will in fact be a structure, a legitimate structure according to the CS. Okay? Because the element of S, and the elements of S must be all the series that instantiate valid classical arguments. Okay? According to certain things that a year ago were not necessary to point out. As a matter of fact, yes, thank you. As a matter of fact, as the notion of series is playing no special role in the definition of this relation, you will have that if you consider modulo permutation, you will also have a structure. If you assume contraction, you will also have it, and if you consider proliferation, you will also have a structure. So you can say that the last one, this one, is a presentation of classical logic, is a Gensenian presentation of classical logic. And now we are using the word not in the air, but in a precise sense. And what is most important here, for what I am interested in, is that I am no longer relying on a relation to a sequence calculus. I am expressing everything, the definition of K was made in model theoretic terms, and now I have a way of speaking of things that come from the sequence calculus in the model theoretic presentation. Why this would be useful? Because now I can use this Gensenian vocabulary even to talk about logics that do not have a known sequence calculus. So for instance, suppose that X is a very unusual logic, but it is defined model theoretically in whatever thing that we want. And to be able to say that it has a Gensenian presentation, you only need to show that you can present it in this way, given that that thing is a prolyset. So if it is a prolyset, it would be a Gensenian presentation of this logic. Whatever strange it is, you don't need a sequence calculus necessarily. What is interesting here is that you can now take the notion of internal substructurality and generalize it to what we are doing here. The definition is a little bit complicated because they won't be direct substructures, but what you want to say is that your logics are related to other two structures by concatenation, and these two structures are, one is a substructure of the other. So if one is a substructure of the other, you say that one logic is a substructural respect to the other. So this is one sense of substructurality. The other sense of substructurality was external substructurality, and external substructurality will appear when we consider things like ST, which we know it is, we want to say that it is substructural related to K, to classical logic, and we know that what distinguishes them is that K is the transitive closure of ST. So, in the definitions that I gave you, it will happen that this structure and this structure here will be externally substructural. And now I have a precise definition that tells me what does it mean to be externally substructural, and I have what I want, that is to have that ST in fact is substructural relating to classical logic. And the third sense can also be recovered. You can consider the relation between a formula and the result of applying a uniform substitution. So this is a relation that holds between formulas of propositional logic. And then you will have that, if you add this to a structure that you already have, you will have a legitimate structure. And so you will be able to say that something is a superstructure or substructure, depending on if it assumes or not the intersubstitutivity of the variable. Okay, one can even want to put this prior in the order of the relation, because remember that the order matters. So you only have to preserve the relations from left to right. Ooh, I have 5 minutes and I want to show you some more things. So we have what we wanted in principle. Closure under uniform substitution is one possible aspect of structurality, and then you will have internal substructurality that recovers the Gaussian tradition and external substructurality that recovers the tradition. Okay, some things about monotonicity. As I said in the beginning, monotonicity is a property kind of weird to generalize. And the reason is because I think we understand it in two senses. In the sense of Tarski, it's a property of consequence relations. And with these things, remember that you are not always presupposing compactness. But in the case of Jensen, there are pairs of rules, and these occur discretely, formula by formula. So to bridge the gap results in the absolute rule that I showed you at the beginning. That was my first observation. And when you look at this from the perspective of ACS, you get the correct way of internalizing the rules of weakening into your calculus. So what you have to do is to define a sequence as a pair of Prodi sets. Now you don't need to write the context because they are completely absorbed by the structure. But when you prove completeness, soundness and completeness, you have something stronger than usual. What you will say is that if you can derive this sequence, you can prove every inference that contains that sequence in both sides because you are using processes. But you don't have the absurd rule as this one because the ontology is not a set that you can create in the theory because the theory is composed primarily of finite sentence series. Okay. Yes, so in a certain sense, the compactness theorem is at the heart of this implementation, of this understanding of logic. And at the beginning, I told you that I wanted to have an abstract calculus theory. And for me, this has two consequences. The first one is that you can extend consistently the talk about the structures in logic to things that are not logics, but this is welcome. But most important, the possibility of studying new substructural and new superstructural logics without the necessity of presenting sequence calculus and without sequence calculi and without the necessity of relying on what we already know about sets and multisets and series, because we can define more structures. I already commented on the first, so I will take a look at the second, and this will be the last thing I will show you. And well, if you take now the calculus for classical logins and calculus for classical logic, you know that it is closed under identity, but all the other structural rules give you all the other relations. That's why I told you that we can put the congruences, the other congruence for permutation, congruence for contraction and proliferation. But if you change this derivation relation by this one, which is the derivation of the one-sided calculus for linear logic, so it goes from series to series, you will obtain something new. And this logic can be presented as a structure, and this structure will be this one. You have all the sequence that you can derive, you have identity between them, you have congruence modulo permutation, and you have the rules of linear logic, or the sequence that you can derive with linear logic. In this structure, if you erase congruence modulo permutation, what you will have is non-commutative linear logic. That thing that Girard called the far west of substructurality. That place that you cannot go here because nobody knows it. But I think that this theory will provide you with means to think of thinner forms of logicality. So obviously, if we drop identity and cut, we will obtain external substructural substructures. So you can have non-reflexive, non-commutative linear logic, non-transitive non-commutative linear logic, or non-reflexive, non-transitive, and non-contractive linear logic, and these are external substructures. But can we go even farther? Can we go even more substructural than this? And if you look at how the structure is composed, maybe you have now an idea of where I am going. The idea would be that I can, if I weaken even this relation. So I am no longer considering the identity as the primary form of preservation of series, of congruence, but I am asking for something less. This structure, it's not true, it's close under identity, but it asks for something more. It has to be preserved downwards. So if you put less things in your series, you have to preserve the relations. And even I can consider this one, I guess no. Today in the morning I was thinking this will really be close under identity. So this is not, but hold on to this one. And the structure that extends this, this with the line above, abajo, has to preserve the relations in a strict descending order. And I will call this kind of a structure Logrian. It's a cheap analogy, and that's why. And you can think that this is too narrow, and you won't have examples of Logrian logic. Sí, ya van a ser. Wait a minute. But in fact, you can. If you consider Fiore-Toranzo-Calderon's logic CL disjunctive conjunctive, what you will have is a Logrian presentation of classical logic. So it is the substructuralist presentation of classical logic that I can think of, because it not even preserves, it also preserves the reduction of the. I have the experts here, so I will have to defend my claim later. Okay, blah, 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 blah. Thank you very much.
Yes, so sorry if I missed something in the presentation, but or many things. But my impression was that you're focusing on particular structural rules that we know very well, such as contraction, weakening, and so on and so forth. But we usually, another way of thinking about structurality is in terms of arbitrary structural meta-inferences. Meta-inferences which just don't have connectives.
Yes.
So do you have or do you want to have some kind of result that for any arbitrary structural meta-inference you can represent properly in your calculus?
Yes, thank you very much for the question, because this is something really important that I wanted to say now. And the fact that in this theory, the reason why you almost only have definitions and very few theorems is that what I want this to be is a framework, an initial framework to think on things like that. But the reason to abstract from the logics is that you don't even are thinking on inferences and meta-inferences in the sense of rules, but you can think them as objects in a very abstract way. So as we think about sets and multisets and series, to add more things to that conceptual family. So for instance, polysets and maybe other things, and maybe eventually, not me because I am not that good a mathematician, but maybe someone with more mathematical preparation can define other things that are interesting and prove things about that things that are interesting, and And then you can go the other way around and think on logics that preserve the structures that you can construct with these other mathematical things. So that would be the idea. So yes, that's precisely the thing that, why I think that this may be interesting. Thank you.
Yeah.
Thank you.
Thanks.
Can you go back to the example of non-transitive noun that you Because I understood the difference between like an external and an internal. Isn't this like a mix of both? Like, why are you saying that they are external structure? Because the fact that they are not commutative.
Yes, if you go to
them
the
internal.
see, if you go to the definition of external substructurality, relation is externally substructured if you have the same prelude. So in this case, you have the same prelude. But the last thing is a relation in which it holds a classical conditional. So everything that happens according to this relation will happen according to this. And probably more things. So as you are dropping rules, naturally what is validated by non-reflexive and commutative linear logic is also validated in non-reflexive, non-transitive, and commutative linear
It's
logic.
okay, but it's like this is like the two ways together. You said you were like going to identify like external structure with non-Tarskian and internal with the other way of thinking.
Not necessarily. Yes.
Okay.
See, not necessarily, because but what will happen is that, for instance, classical logic and ST, the substructural relation that holds between them is an external substructural relation. Because in fact,
SD is non-transitive.
yes, because it is not transitive, so you can have the same prelude, you can consider Crowley sets, because both are monotonic, but when you compare them vertically, so to speak, you will have that in classical logic, you have everything that you have in ST and probably more things. From a very superficial way of looking at it. Because we know that ST can be applied to other things, but in principle, just by looking at the definition of the consequence relation, the external substructural.
I understand. We can talk about
Okay.
but I still don't understand this one. Okay.
Thank you for this talk. I like it very much. It's my addition also. And I want to ask you about category theory, Yeah, you know some relation with the category theory?
I was thinking about this because some of these operations, the concatenation and some of the relations will have the associative property that you would ask to create a very simple category. Although I am very understood on the matter, but I have the suspicion that if this gets translated into category theory, it may be much more useful because I can get more abstractness and import other results. But what I would, what I don't want to lose is the connection with logic. So I am afraid that if I'm going too abstract, I will have something that is completely so abstract that it's maybe not that related to the specific application that this is supposed to have. So I don't know, but yes, I think that category theory and maybe other theories are suited to embrace this and present this as an application of these other theories. Thank you.
Yeah, thanks for that. I like it, but I think there is a point that you didn't take into account, which is that the tradition from Ono and all these people, they take some structural logics to be induced by residue lattices and so on and so forth. And as a consequence of that, classical logic is a substructural logic, whereas our tradition does not take classical logic to be a substructural. So I doubt that there's going to be a definition that will, pay homage to both of them. What do you think?
Yes, thank you. I am I am not very expert on the algebraic things, so maybe what I am going to say is plainly false. But this is an arbitrary. The definition of Geretsenian is arbitrary. So, and the spirit is that. What is it? What is it? It doesn't matter. The point is that when I say that something is Geretsenian, you can have superstructures because you can add more relations to the structure. So this is an arbitrary point to make the cut. So you can present classical logic as a structure in this sense. So you will have the precise definition of why it is Geretsenian, but see that the relation of super and substructurality does not have a zero, so to speak. So I am not trying to say that classical and inclusionistic logics are structural and all the others are superstructural according to them, but it is a relational comparison. So if I can take this algebraic presentation of other things, of the residential lattices and so on, and obtain them as structures in this sense by adding more elements to the Prolyset structure, to the definition of Prolyset, then I would harmonize that with this claim that classical logic is in fact substructural. Thank you.
Yes, thank you. It was super nice talk. I have some things I thought. So first of all, I mean, calculus of structures is interesting as a name because, as you might know, it's also the system, so the calculus that is used in the deep inference community, like the actual calculus. So deep inference means like the method, and the calculus that they have usually is called calculus of structures. And there the point is that there are no structural rules. It's like there are no structures like commas or anything. Everything is a connected. So, and also I think like this looks like more like a theory of structures, I think still. But you said you had something in mind. But yeah, the thing mostly I wanted to say about this is, I mean, I think you can do a lot of stuff with this. I don't know if you have thought about that, but I mean, it's also that I think it's a little bit more complicated than you presented in a sense, because many funny things happen with structural rules. For example, weakening can be completely, other than with generalized identity, you can get weakening inside the system as absorbed just by having additive and multiplicative rules altogether. And then you get the only weakening that you lack is the kind of external weakening. So like the things such that gamma implies delta if and only if there is a derivation between subsets of gamma and subsets of delta in a sequence calculus. So this is resolved by Hughes some years ago. And another funny thing is that if you take the non-permutation, so like this non-commutative calculus, LK, and you say that weakening can happen only at the end of the list, you can embed LJ. So you can get intuitionistic logic out of LK minus permutation on the right, and other things like this. So I mean, like maybe you might want to have, like when can I apply proliferation? Maybe at the end of the set, of the list, like this kind of stuff.
That is very interesting because thank you for the comments. This is very interesting because in fact these are just the definitions that I thought for the moment, but obviously you can define a lot more. You can define, as you said, proliferation in the case of series and not multi-sets or not series. You can say not sets, and you can define even other perhaps weirder versions of operations between series, but the important thing is that in any case, what you will be able to do with that is to define a certain relation and then to flag a structure. See also that in my definition of structure, definition A, by the moment only considers binary relations, because I don't know how to define the substructurality when the substructural indicates when the relations are non-binary. So that's a lot of things that I can, all of course, relativize and obtain more things. So yes, obviously this is supposed to include in the future more things, or it is the aim is to serve as a starting point to do more crazy and
yeah, just
unexpected things.
yeah. Other two things I think like you can look at would be super interesting to have is to represent more complicated sequence structures. So like hypersequence and nestings. That would be very interesting to have.
Makes sense? Yes. Seriously.
Yeah.
Okay, thank you. Well,
Yeah, so basically the question I had is the one that earlier just asked. I mean, when you say superstructure, right, it's a bit unclear whether you mean something like a weaker, more general structure than a set. It's a bugger to find one of those, right? Because there's nothing to them but extension, right? So no structure. But you might also mean something like, a richer structure, which, which essentially brings about things like three structures, hypersequence, all sorts of things. I just don't really get the motivation for bringing together all three senses of substructurality. I mean, if I look at the first two, I happen to have strong opinions about at least what I mean about by substructural, but I also think that it's essentially a verbal dispute. And if you want to use substructural to mean subtaschian, you're going to be a mild irritation because I had to write a footnote about the fact that I'm not using it in that sense, but that's fine. Yes, the dispute is purely verbal. But I don't understand why would you want the Polish sense of structurality, so to speak, the closure and the substitution to be there as well. I mean, I should think that on the contrary, we want separate words for at least the first two and the third. Or, just disambiguate.
I agree that this may be thought as a verbal dispute. If you read the abstract I put in the webpage, it says precisely that. But philosophy, I think that this is a philosophical choice that we all can make, that according to Wittgenstein, everything is a concept of terminological excuse. So yes, you can take that road, but I think that sometimes there are certain concepts that are interesting, and if there is some fertility in considering an explication that encompasses the uses, it is wise at least to try it. And so the things that I showed here, maybe they are not convincing to you, but what I try to do is to show a way in which this encompassment may be of certain interest. For instance, I found that one of the weird logics that Camilo and Joaquin work were substructural and very substructural according to my definitions. So I don't know. At least for me, that is interesting.
Cool.
It's a question because I'm trying to understand what you explain. How to define linear logic again is S, where S is what an equality, and then
the reason why there is never there are no. Oh, Eduardo, can you give me the control? The puntero back?
I suppose so. We don't have employees.
Okay, no, it doesn't matter. It doesn't matter. It doesn't matter. When you have things like this set is supposed to be filled with the relations. So it is not a nest. There will be all the sequence that you can prove that are validated according to whatever definition you use. See, so
yeah, but in linear logic you have weakening contraction if you have that. So where is this there?
Yes, but you will have for instance that so this will be something. This series will be decided. Okay, is the premises and the conclusion. One instance of final. Now, if I remember, I can directly here, right? I can put a interrogation point here. Yes? Is that it?
Yeah.
So this one is also in the set.
Yeah.
This one is also in.
I know, I mean.
But it is not that you are applying it is not this is not the same as for instance, this one, that would be the application of proliferation in the right hand side. It is not the same.
Okay, I think we're late and now
Okay.
that's fine, thank you.
One question. What's the names? Thanks a lot.
Ya, yo te voy a pagar los viajes. Pero no está seguro. Y me miró porque se lo voy a hacer la mañana. Chao. Si quieres cambiar,
Okay, now final thoughts for this two very long 2-week colloquium by Maria Ruiz. We're talking about no import, export. Thanks a lot.
So this would be a brief talk. Whatever. This is a work in progress. Actually, there are some results and then there are some price for help. What I'm going to do today is talk a little bit about Shivard's collapse result. It's a result regarding indicative conditionals. And what I will show is that usually one thinks that certain assumptions are needed, and I will simply show that one can derive the same results with less assumptions than what is usually thought. And then I will ask for some help. So let's start. At the beginning of the 80s, Shivard proved the following thing. I will present it a little bit better afterwards, just to have a brief introduction. What he showed is that it is not possible to expand the language of classical logic by adding an indicative conditional that validates more components, imports export, which is this equivalent, and that is strictly stronger than the material conditions. That is, it validates more components and import export, then it collapses with the material. As a result, you have to accept that either the indicative conditional is the material conditional, as Williams formulas or other people, or you have to invalidate either most one of the important. Work for it. A few years ago, I talked a little bit about this on Friday for those who work here. Michelson proved a stronger result in which what he shows is that you don't need to assume classical logic. It will also lapse for the intuitionistic logic. Actually, for the positive fragment of intuitionistic logic. So it will collapse to infinite logic. Now, what I'm going to do today is to show that the collapse can be derived without assuming that either conditional, neither the conditional from the logic nor the indicative conditional validates effort. That is, instead of using this equivalence, I will only use one side of the equivalence. I'll do it twice. The first, I will do it with a set of rules that are neutral with respect to the rest of the language. Usually you have to assume certain stuff about the conjunction or the disjunction and the negation. I will do it without assuming anything about the rest of the language. And the second time, but I mean, I will use some assumptions that are less controversial, but still weaker than the usual assumptions. The corollary is that if you need both import and export to make the indicative conditional collapse with the intuitionistic conditional, then the indicative can collapse with even stronger conditionals. I will speak a little bit about this in a second. Mainly the indicative conditional collapse in weaker logics. And I will talk a little bit about how to avoid the result by restricting some structural rules in the name of places. So, a little bit of terminology, just to avoid confusion. Right squig arrow is the indicative, and the normal right arrow will be the conditional of the base logic. Base logic is just the logic without any conditional logic. The one with the conditional, and this could be like B dash B. I just did it this way and then didn't change it. So one thing that is important to mention, because it's quite confusing, it took me a long time of it's really confusing, the terminology. To say that the conditional is stronger than the material conditional, here we will mean that the indicative logically implies, whatever the logic is, the indicative implies the material. Why is that? Another way to think about it is simply what you actually want when you're doing conditionals. The most important thing that you want is that your conditional might be false in some cases with false antecedents. So that's pretty much it. That's it. So now the introduction, and I will speak a little bit more about the actual collapse result, and then I will show what I did. So in the XII I proved that the following 5 assumptions make the indicative collapse with the material. In particular, import-export. Import-export is a really important inference or equivalence thing when you do conditionals, because it's kind of the thing that allows you to translate nested conditionals, which are a weird thing, into something that we can understand. And that's why pretty much everyone wants import-export. Strong 11, I already said what it is. Then this is a really weird assumption. This is how Shivak puts it. I will read supraclassicality as follows. There are certain classical instances, classically valid arguments that you would like to be a tautology when you change the term style to an indicative conditional. That's how I would read it. Otherwise, it's a really weird assumption. So it's not. And then he assumed that the conditional of the base logic the conditional of the logic. She assumes the material conditional that you have it on the language, and intersubstitutivity in the antecedent for equivalent sentences. Which in classical logic, it's reasonable, you wouldn't want it to keep it that way if you extend it. Anyway, this is not important. With these 5 assumptions, you have an immediate collapse. A few years later, Wilson showed that you don't need to assume classical logic, you can just be a little bit more, only by assuming these things, the conditional will also collapse in the intuitionistic logic. In particular, he assumes several things that are really reasonable, conjunction elimination for both conditionals, import-export for both conditional, one stronger than, which was one of the things that we wanted. Conjunction introduction, one side of the most one side of the deduction theorem, and left logical equivalence. A few years later, he uploaded a note on his website showing that you could also, that you could even prove it with less assumptions. In particular, this is for Python expert, with this proof for the indicative, sorry, assuming import for the conditional of the base logic, either the intuitionistic or the mathematical. So, just to be brief about this, what I will do in what follows is show that if you also accept Faitelson's expert, then you should also accept the similar rule, which I will call structural expert. That allows one to derive the collapse without assuming anything regarding the conjunction. And then I will show it with real expert. And in both cases, you will have like a result that is a bit stronger than the ones that are in the literature because they have less assumptions. And I'm pretty sure those are not the intuitionist, that is not enough to recover intuitionistic logic. The question that I will leave open is what is that? And that's pretty much what I would appreciate your help most. So first, the first derivation, let's take this. This is not like that. This is the less amount of assumptions that you might want to have in order to, that you have to accept as far as I know, in order to make this collapse. So this system has identity for complex formulas, cat, the regular rule for the left rule for the conditional, and then you have these 2 rules. Stronger than the conditional of the base logic and this structural export, which is pretty much the same rule as Python had, but with a comma instead of the conjunction. I didn't use any context here to make it as strong as possible. We will see what happens if you add context later. So the derivation is immediate, to be honest. I don't know if you want to write it. You just make modus ponens, use the 2 rules that the structural expert that is stronger than, and then you pass. So those were the multiplicative rules. One could derive the same result by presenting it in an analytic manner, but then you have to add the weakening. I'm doing everything with single conclusions because it's easier to show that it might collapse to intuitionistic logic. And then again, you only have to put some things here. I did everything with sets, then I regret it, but it was too late. Actually, like Camila told me, it's like 2 months ago. But only for comparing with other logics, it would be more useful to have multi-sets or sequences. I didn't do it with sequences or multi-sets because contraction is not a rule that is really important in the literature about indicative conditionals in particular. That was the only reason. Now I regret. Anyway, so plexus moment. Weakening is such an easy show. I will step in having plexus everywhere, and I will be the queen of comedy. Weakening is usually a controversial rule when it comes to conditional logic. There are many theories that are non-monotonic, some or other cells. There are usually non-monotonic, nevertheless, regarding the conditional fragment. And in this context, you still like, you use for another rule that is usually challenged in the literature is exchange. I didn't use sequences here because I don't understand why you would want, like, in particular, the way I presented the rules, you don't need to use exchange at any moment. But well, if you would change the order of the things in the CAT formula or here, you might want to use it, but I don't understand quite well what the motivation to do this in a conditional logic in particular, so I simply avoided it here. And then there are a lot of cases like general dynamic logics. Some of them, at least the ones that I know, are non-reflexive, and that's the way they avoid the collapse. So what is this thing? Is this enough to recover impressionistic logic? Well, in principle, I don't think so, for several reasons. First of all, we don't have weakening here. Second, if you add context to this rule, then you can add a structural import version of the rule. Which, if we were to have weakening, I think would be enough to recover the inclusionistic fragment. But because we don't have it, I don't know. Also, I couldn't come up with a rule. And that's pretty much the first part of it. We have a set of rules. I'm pretty confident that it won't collapse to the inclusionistic conditional, but a weaker one, but I don't have like a general proof of that. And I don't know how to do that. But nevertheless, one has to accept that S export is dubious law. In particular, if you could prove any theorem with this ERT theory, and you had left weakening, then you could prove some kind of version of the parallels of the material conditional, of these parallels of the material conditional, which is part of the things that we were trying to avoid when we started doing a logic for conditional or thinking of the semantics of indicative conditional. So I will now present you the same thing, but this time with the export rule instead of this structural export, in which we will have to assume a little bit about conjunctions. So this is pretty much the same as before. We have identity, we have CAT, the left rule for the conditional of the base logic, stronger than, and here we have export, again, no context to make it stronger, but whatever, and this axiom. So this axiom is kind of like an instance of supraclassicality. It's an axiom that tells you that something like you indicatively accept that your material conditional by your small components, which I don't think is really complicated. It's really polemic, like controversial. I know. But if you have this, the collapse is immediate. And again, the question is, what is collapsing with what? Again, remember, we don't have weakening here. Well, so the proof that Faitelson does uses this particular axiom instead of the one that I showed you here. I mean, this is like mode phonons, like a really pure version of mode phonons. And this is just conjunction elimination, which is less polemic. And it's almost valid, it's valid in almost every logic of conditionals, not my thermons. I read it and I found one that is invalid. And if you have this axiom instead of the one that I presented, one needs, and if you also have important weakening to the left, or if you have the rule for the condition of the base language, then you can, it's not that hard to show that you can make it called that object is intuitionistic logic. So that conditionals, the both conditionals are already collapsed, but now if you add this rule, then that is the intuitionistic conditional. But I still think that the one that I use, with this weird axiom, is still weaker than intuitionistic fragment for the conditional. But again, I'm not really sure how to prove it. So it was short, 17 minutes. It gets shorter every time I do it. So some final remarks. The question for what is the upper bound for the strength of the conditional to collapse is of particular relevance in the region. Chibar's theorem seems to show that one either has to accept that the indicative conditional is a material or one has to reject either mode components or import text. Faitelson's remark tell us that you don't need to accept the collapse to the material. You can go, you can accept that it collapses with intuitionistic conditional. You've heard me talk about this, or maybe not, but that's my position. Nevertheless, I think maybe we are kind of rushing into accepting one of these consequences. In particular, it's not that you can validate most mandatory for export. You have to invalidate all funnels or export. Of course, if you invalidate export, you're invalidating import export. But you can't invalidate either both any of import or export. You need to invalidate export to avoid the collapse. And also, it might be the case that there is some interesting logic in the middle that is weaker than the intuitionistic one, and that is also in which it also collapses. And it might be interesting to see what happens in that object, like in a more substantive thing, not just with this really reduced set of assumptions. That's pretty much it. This is my favorite collapse.
For questions, I mean,
She's collapsing, mentally collapsing.
So we said that if we survive this, then we can survive the collapse of the indicative conditional.
And we can also survive this huge workshop.
Hey, no, so I have an actual question.
Okay.
I'm gonna go back to the first calculus.
Yeah, the one you like.
Yep. So I want to see that. Okay, so now I think that I get, it's a practical question. Now I think that I get what are you aiming at with this part of the discussion? You're trying to see if actually the full power of intuitionistic logic is required or maybe not for the collapse. So I think that technically speaking, in this setting, this will boil down to whether or not in this thing, the right rule is the right one or not.
Exactly.
So that's a technical question that needs to be answered, and it has an answer. It seems that someone has an answer.
I believe it was answered. So
the reference that springs to mind is actually Prenozel. Now he does it in a different calculus, but I believe if you have the left rule, so the elimination rule as it were, and yeah, if you have identity and cut, then the right rule is the right rule. Not the right.
With this and what else?
Yeah, from that and identity and cut, I think the right rule is at least admissible.
Yes, so that admissible might be the case, but the regulation, right? This we have been discussing for the past few weeks / months with Mario and all of you. Admissible for sure. Question is, right? I think that's the point that Mario is trying to aim at, right?
I mean, I was thinking about the livability.
I mean, if the right rule is available, if the right rule is available, you have inclusionistic logic. So.
And we know that with context here, and if we were to have a weakening to the left, that would be the diagonal.
For sure.
The question is without the.
Why there is no invertible because that one's not invertible. But how about if you move to the invertible version of the left? So single context. Yeah. Swap. Assume that gamma is the same as delta, and then collapse them in the conclusion. And then that means that the inverse is that one. Because that's going to allow you to add, for instance, the inverse of that to your system, and then I believe you have both cut and identity. You do get the livability, but it's 8 today, so my brain doesn't work.
Wait, so Mario, I think that what I would like to say is that I think that now you made very clear what is your problem / what are you inquiring into with this specific calculus. I mean, you want to know whether or not Faiselson's statement is accurate or whether he overstepped a little bit.
Yes.
And now I think you have made it pretty clear, and I appreciate that a lot.
Thank you. Yes, that's pretty much the question. I wanted to know. Nevertheless, this is true, no? That without the rule for weakening, there's still something missing. And even if you add context here, and you can, like, if you take these two rules, and you put the right rule for this, you still don't have the nutritionistic problem, the conditional nutritionistic problem, because you still need the weakening. Or valid here with subspace, no?
I would say that, I mean, it depends on how so remember.
Not with this.
I mean, of course, there are specialists, RGs, more special than me in the room, but remember that if you have some special combinations of the left and right rules,
yes,
then weakening would be right. So.
This doesn't something I would have. Which are the combinations?
Well,
because I don't remember.
Some sit downs maybe and trying to figure it out.
You don't have the rules that will allow you to derive like a weakening and contraction. You don't have the right combinations.
Then would be the additive.
Yeah, so you would need, half of it to be additive, the other half to be multiplicative.
Okay.
That's safe.
Super vague. At some point you said that the rules have no context to make them stronger.
No, to make the assumption stronger. To make the result stronger. Sorry, yes, I keep on doing this. Make bigger assumptions, so to make it stronger. Yeah. Yes.
We're talking about
what? That was my question, but it made them weird.
about the export in the context of in general, but that derivation, you have taken in theorem, apply weakening and export, you will have theorems with conditional flow. What about restricting export and forms of varieties factors for branches that just not include weakening in any way? For example, like my work here, I don't know if they work in the minimal version of the smallest version.
Here it's kind of absurd weakening. But this is like the minimal that requires weakening.
Yeah, that's an answer for that. So, but not an answer for the minimal. For the minimal version.
But again, I maybe I didn't understand this question. But
Where is absorbed cut here?
Cut or
sorry, weakening.
I think here.
Okay, can you go back to? Okay.
So usually you would have to yes, here. And also in cut, like the way cut is presented.
Well, if that is the case, then you can present a version of base export that is restricted to.
So you say, okay, I see what you're saying.
That applies only to branches that don't include cut nor.
You mean that you want to have to avoid this paradox?
Yeah.
Yes. I guess that would be a nice something that someone might want. As a matter of fact, I should check this, but one should see, for example, Giddy's logic, and it's probable that it works in that sense. For example, in some sense of working in that sense, in the meaning that usually it's non-commutative and non-monotonic when you are in the context of conditional. So it's probably one of the ways they use to build the result also be reflexive.
And if those rules also absorb cut, then you can extend it to those cases. To the simplest version.
What do you mean by it?
You said that, can you go back to you said that this rule absorbs cut. We can.
You say if you not to use as export, if
Yes.
it comes from a branch that use this one. Okay. Yeah, that means fine.
Okay. Does anyone have a question? Okay. Probably on final. You also have a question?
I have a detail.
Two last question, Bruno and.
Yes, my question is about the rules.
Yes.
Can you go back to the rules? My question is about what is the collapse you are looking for. I mean, in this formulation, you're looking like the other way around of the SPR, or you want like the expression, the probable sequence.
Sorry, can you repeat the beginning of the question? I didn't hear.
In the way I mean, maybe it's but you can formulate all of these in many ways. Like for instance, STR, you can put the thing on like a last axiom, and put all of these everywhere. And if you have a context, and you have many possibilities.
Yes.
So the answer to if you are looking for an admissible rule or a derivable rule depends on what you are looking for to have, which equivalence. To have this meta rule as a meta rule derivable, or like to have the probable sequence as a probable sequence. And in that one case, you only need an admissible rule, and in the other case, you need a derivable. So how many answers?
Yes, you're right. I tried a little bit of both. Like I know where I have several proofs of the admissibility when you add certain rules, but then with this short amount of rules, I couldn't derive it. No, I couldn't derive all the probable sequence. But maybe I'm just short of imagination or of practice. That's the main concern. So I thought about looking for the semantics for this. I don't know. I will put some effort on that at some point in my life.
No, see, I am completely sure that you know that, but could you go to the case that you call the modus ponens? Yes.
The axiom, the weird axiom.
Yeah, exactly.
Yes.
So you need this shape of modus ponens, not the other one, the rule, the traditional rule of modus ponens. Is important this distinction in this context?
Yes, because the thing is that you need so you need to start a proof that involves transactions. That's why.
So you need to be.
And indicative conditionals. So you need some axiom, at least one, that has an indicative conditional and a transaction. It doesn't have to be this. This one was the one that allowed me to derive it without assuming extra stuff. But well, for example, you can use this, or there are several others actually. But the simpler the axioms, the more roles you need to derive the labs. It's just to start the proof. Yes, at least as far as I could imagine.
Okay, thanks a lot, Mario. Il gruppo di organizzato Fabiano, Eduardo, Lucas. Any questions? Everyone for the introduction. Hope to see you again next year. Let's go to have some beer.
Yeah.
Ciao, ciao.